Okay, this first one up here, can you tell me what unit we've got, what we were given? What parameter this unit is measuring? So those are the units. What's it measuring? Second? It's measuring density. Do we see that? I basically have a mass unit in the numerator and I have a volume unit in the denominator. So we're measuring density. Who would ever be measuring density of things in tons per cubic yard? Why would I want to do something that was that massive and then that large? Could be concrete, building a dam or something like that. Could be mining, digging soil out of the ground, trying to figure out the density. What would the density of dirt coming out of a mine be telling you? Yeah, I mean, if there's gold in the soil, then the soil will be more dense than some soil that doesn't have any gold in it. So it might seem insignificant that someplace in the second decimal place or something like that in density of soil is going to tell you something, but it's very clear to a mining company that that soil is going to have precious or semi-precious metals in it, as opposed to just organic matter. Okay, so I'll go ahead and start with this 2.34 tons per yard cubed. And I need, what do you want to convert first, the tons or the yards? The tons? Okay, so what did you come up with for tons for unit conversion? 2,000 pounds is 1 ton. Okay, so my tons cancels out, and what do I have next? Okay, so I'm going to need to put the pounds unit in the denominator, and that'll be 2.2, and then that'll be 1 kilogram. And then I need a kilogram down here, and so there'll be 1 kilogram, and it'll be 1,000 grams. Okay, so I've got the unit in the numerator that I'm looking for, the grams unit. So what I need now is to figure out my denominator to get the yards into centimeters cubed. So what do you want to do first? The yard needs to be in the numerator, right? What do you want to put in the denominator? Okay, sure. And so now I have feet in the denominator, so I'll put feet here and I'll put inches here, 1 foot and 12 inches. And then the last thing I need to do is go 1 inch. And then what was do you guys remember the conversion over to centimeters? Yeah, 2.54 centimeters. Okay, so if I do that, am I good? Yeah. When I put this yard unit in the numerator right here, what does that cancel in the denominator? 1 of the yards, right? So this yard cubed is really a yard times a yard times a yard. So what I've been able to do is cancel out 1 of these yards because I put it up there once. So if I want to cancel out all 3 of the yards in the denominator, I can do 2 things. The first thing I could do is I could do this again. I could write all of this 2 more times. But that seems like really long, right? So what's the other thing you could do? I could cube it. I can actually write 3 for a cube. I'm cubing the yard and the feet and the 3 and the 1. As long as everything gets a cube or a square or whatever it is that you want, then you're totally fine. But make sure that when you're punching this into the calculator, that this isn't just a 3, this is 3 cubed. So now that everything here is cubed, what can I do over here? the whole thing gets canceled out. So this yard cubed is gone. All right. So I'm going to need to do that with all three of these conversions. So my second conversion factor, 3 for the feet, 3 for the 1, 3 for the inch, and 3 for the 12. And then the feet cubed are gone. And then I'll cube the inches, the 1, the centimeters cubed, and the 2.54. And then the inches disappear. And then the units that I have, or the units that I want, which are the grams and the centimeters cubed. Okay, so what do we got here? 2.34 times 2,000 times 1,000 divided by 2.2 divided by 3 cubed divided by 12 cubed and divided by 2.54 cubed. And I got 2.78. And I got 2.782, but we only have 3 significant figures with the 2.34. So then there's my answer, 2.78. Questions about that one? That's about as hard as a unit conversion could possibly be, for us at least. Okay, so this new one, or this next one here. The density of water is what? All right, so water's density is 1 gram per centimeter cubed, or 1 gram per milliliter. And if I want something to float, the density of the other object needs to be what? Less than that. Okay, so my density of my phone needs to be what? Needs to be less than 1 gram per centimeter cubed. So what I know is I've got a mass of 180 grams. And then centimeter cube number. What centimeter cube number would I need to put there to make my density of my phone and my bag less than 1? And there's lots of numbers I could put down there, but give me one that would work. No. Any number more than 180. So if I put, I don't know, 190 down here, my answer is, my density of this is going to be 0.9 something or other, right? Is that going to float? Certainly, that will float. So the answer for this one is any density that's greater than 180 centimeters cubed. And yeah, this actually happened to me. And I will tell you that it is less than 180 total volume. So there is an iPhone 3S at the bottom of the Columbia somewhere. It's been there for like 6 years. If one of you find it, it's mine. I'm sure it still works because the case is like really good, but it's down there. All right, what makes this? I shouldn't put both up there, but sorry. We hadn't gotten to the other part. What makes the Greek theory of the atom a big jump forward?
Starting point, basic experimentation.
Okay. So what did we say about the atoms? So if I understand that atoms If I understand that atoms are building blocks, then I can base experimentation off of that. It is your starting point. So to make that a little bit more clear, can somebody tell me what the elements were during this Greek time period? Air, fire, earth, and water. Is that everything made up of those things, right? Tristan? I could not, I could not actually care at all. Anyway, if it is, great. But as far as the chemistry stuff I mean, is stuff made of earth, air, water, and fire? No, I mean, it's silly. Fire isn't even a substance. Fire is a chemical reaction. It's the plasmification of whatever it is that is under a chemical burn. So you can't build experimentation off of something that is fake, right? So if you're trying to draw up an experiment, I mean, what kinds of things, what is the big classical chemistry style experiment that people were trying to use based off of these 4 fundamental or 5 fundamental elements? What were pseudo-chemists trying to do for thousands of years? Trying to turn metals that were not precious metals into precious metals. So trying to convert lead into gold. So trying to build an experimentation off of that and not understanding what gold and lead actually are. And you're thinking that it's ether, air, fire, earth, and water. It's not going to work. I mean, it's never going to work, actually. You can't chemically convert one of those things into another thing. But you can't understand that your problem and your premise, you can't understand that your problem is unsolvable because your initial premise is completely incorrect. If you're trying to solve a problem and you don't understand what the problem is, then you're never going to solve the problem without, just blind luck. Okay, this next one, magnitude of the charge of the proton and the electron. They're equal to each other. Even though the proton is like 1,800 times more massive, the charge, the plus charge, is actually directly equal to the minus charge. Their size are exactly the same thing. So if I've got a hydrogen atom and it's got 1 proton and 1 electron, what's the charge of the hydrogen atom? No charge, 0 charge. +1, -1, no charge. They cancel out. What was it that Thomson had discovered about the atom? Okay, I like that. Divisible. Is that an A or an I? I feel like it's an I. I usually say that he realizes that a part can come off. But yeah, it's divisible. I can separate the atom into different components. And what component did he separate it into? What did he get out of it? He found an electron and something else. He found the electron and that the electron was negatively charged. And so then the something else must have been positively charged. Don't put the plum pudding model down with this. That was his theory, and that's actually not correct. The things that he determined about the atom that are correct are the fact that they're divisible, there's a negative charge, and there's a positive charge, and that's what he knows. And the negative thing can come off. How about Rutherford? What did he come up with? Okay, he disproved the plum pudding model by doing what? What did he say? Basically, we're talking about this part right here, right? This something else is what he determined what that something else was. And what is it? He came up with the nuclear model of the atom. And the positive part of the atom is in the center. And can you tell me something about it, that center? It's very dense. It's really, really small. And something else? He confirmed that it was positively charged. I guess I already said that, the positive center. All right. How about Soddy? We talked about him for like 2 seconds, but What did you find out about him? That's Chadwick. That's this guy. So, what did Rutherford not discover about the nucleus? Yeah, okay, he definitely didn't discover neutrons, but he also didn't discover something else really important. They didn't discover there were protons there. He just thought it was a chunk of positive mass. I mean, he didn't really think that, but he didn't have any indication that there was anything else there going on. So he brought Frederick Soddy in the same way that that Thomson brought Rutherford in, and Soddy worked with him until they figured out that the nucleus isn't just a chunk of really small, dense positiveness, that it was composed of protons. So and then what'd you say about Chadwick, Dana?
No, you want to say it again?
I did totally want you to say it again.
Discovered isotopes or,
Sure.
same elements of different masses.
Discovered isotopes, which really means he discovered the neutron. So they're going to have the same number of protons and different numbers of neutrons. Why did it take 33 years for this to be figured out, that there were neutrons? One, no one's looking. And what else? Sorry? It has no charge. So the magnetic field and electric field, they didn't do anything at all. They don't do anything to something that's got no charge on it. So the things that we were using to study the electron and study the proton weren't affecting the neutron, so we never noticed it. Okay, so these isotopes we have down here. If I have something and its symbol is beryllium, or Be, its name is beryllium, but what's its atomic number? 4. Yep. So if I've got 4 protons, my symbol is Be. If I'm Be, I've got 4 protons. If I have 4 protons, I also have what? 4 electrons. And so then this 4 and 6 equals 10, so that makes sense. That's what we would expect out of the mass. It's the protons and the neutron number. It doesn't actually say that. What does it say? 9.01. So remember what we were saying about those masses? So why is it not like 9 or 10 or something like that? Why is it 9.01? The total average. So if it's 9.01, that's telling you if you grabbed a beryllium atom and looked at it and massed it out, what mass is it probably going to be? It's going to probably be 9, because 9's if I'm taking the average of all of them and the average is really close to 9, then the chances that I just grabbed a beryllium with a mass of 9 is pretty good. But could I have grabbed a beryllium with a mass of 10? Absolutely. Could I have got one with a mass of 8? Yeah. Could I have got one with a mass of 7? Probably. I don't know exactly how light the beryllium gets, how many different variations of the isotopes there are. For the hydrogen, I know I could get a mass of 1. I know I could get one with a mass of 2. I know I could get one with a mass of 3, and then there aren't any other versions of it. If I'm talking about a really big atom like uranium, there are about 40 isotopes. So they all have the set number of protons, but then the number of neutrons varies. The larger I get, the more variation I can have in my neutron number. So is it possible to get a beryllium with a mass of 10? Yeah. This one just has one more neutron than your typical beryllium does. So if I've got something with an atomic number of 82, what am I looking at? Lead. And lead symbol is what? Pb. Since it's lead, it's got 82 protons, so it has how many electrons? 82. This isotope of lead has a mass of 207. And I know that 82 of that mass has to be protons. So then how many neutrons do I have? 35? 125. Okay. So OS is osmium. Not a very common element, but it's really, really dense. So the osmium atom has how many protons in it? 76. So that means it's got 76 electrons. And if this osmium has a mass of 190, then what is the neutron count for this guy? 114. Okay. So if I have radium, I've got Ra, that's element number 88, right? So that means it's got 88 protons. And so if I've got 88 protons and electrons, and I've got 138 neutrons, then I've got, what, 226 for my total mass. Okay.